And we will basically move immediately to the first keynote that is going to be given by Josef Šivic. Josef Šivic is a distinguished researcher at the Czech Institute of Informatics, Robotics and Cybernetics, which is right next door here. It's part of the Czech Technical University. And he's also with the ELIS unit Prague. And he did his PhD in the University of Oxford. And he did his postdoc at MIT. And he got a habilitation at the École Normale Supérieure in Paris. He is right now the awardee of an ERC grant. That's his second ERC grant. And yeah, he's working on, of course, several topics. And today, his current topic, his main line is learning manipulation skills from instructional videos. So, Josef, thank you for coming, and floor is yours.
Thank you very much, Matěj, for the very nice introduction. It's really a pleasure to be here. I'm also from Prague, from just building next door. So welcome in Prague also. I hope you enjoy the stay. And so today what I will talk about is our recent work in the area of robot learning. And I will show a lot of work which we do on learning these manipulation skills and working with instructional videos. I will start a bit more broadly. So my background is really computer vision. Computer vision is about extracting information from images. And as you saw in the very nice, in the video which Matěj was showing, I find computer vision very exciting because cameras or visual sensors more broadly, or depth cameras, are now sort of placed on many of the systems which interact with the physical world around us, like the robot from the Boston Dynamics, which you see on the screen. And they enable these systems to perceive its surrounding environment, interact with it. And I think the point which I find the most interesting almost is the perceive also the outcomes of the interaction with the environment and learn from those. So it's perceiving, interacting, but also learning by seeing the outcomes of these interactions. So, and why this is exciting, and Matěj was touching on some of these sort of potential outcomes. Well, imagine just for a moment, we really did have robots which would have the same level of manipulation skills as humans. So that would be a revolution in manufacturing, for example. They could go also to places which are dangerous for people, or they could teach human sort of novices how to do things. But there would be some other implications. So we really had, big thanks to machine learning, we had sort of a huge progress in diagnoses of diseases. But imagine if we did really have these sort of machines which could interact with the environment on the level of humans. We could also have automatic surgeons, for example, which could potentially, and we saw it in diagnoses where we have accumulate information from many different medical experts, we could potentially surpass sort of the individual experts. So imagine we have surgical robots which would be better than some individual surgeons in performing surgery. So I think these are sort of very exciting prospects. But of course, we are not there, as Matěj mentioned. We are potentially far from this. What we do have, though, are now systems. We've seen huge progress in natural language processing. So we do have these systems, as you probably have also or are using maybe on an everyday basis, like the ChatGPT, which are amazing. These processing of a natural language. I show here some examples. This is a few years back from some benchmarks. The particular one which I like is the first one, uniform bar exam. So this is an exam if you want to perform law in the US, you have to pass that. And this, I think this is the GPT-4. Not only it did pass the exam, but it did it better than 90% of people, of humans. So we have these amazing abilities in processing natural language. And one of the key factors in obtaining these abilities seems to be a huge amount of data. So I'm mentioning this GPT-3. This is even the previous, or maybe almost we have GPT-5, previous generation of systems, where they are trained on hundreds of billions of words. So I translate it in this case to, it's like more than 600 million pages or 2 million books of text. So we have these amazing systems processing natural language, yet we don't have a system which would be able to reliably empty a dishwasher, or which would have skills in kitchen, cooking skills as a 10-year-old. So why this is interesting? It's not new. So you probably know of Hans-Peter Moravec. So he was already back in 80s. He sort of noticed that it's relatively easy to get computers to do intelligence tests or playing checkers at his time. But when it comes to perception and mobility, it's difficult or impossible to give them the skills of a 1-year-old. So of course we've progressed since then, and I'm looking for interesting discussion with you why this may be the case, why we have this gap between, which we sometimes call Moravec's paradox, between these visuo-motor skills which humans have and some other more abstract thinking skills between humans and computers. So, and here the hypothesis, which may be true or not, and I'm very happy to discuss with you, but one thing which we do know is that in the difference now we have with the natural language and what we have in robotics is the training data. So in natural language we have these huge amounts of training data, which we just don't have. So I will structure the rest of the talk around different directions which could enlarge the amount of training data which we have for robots. So I picked these three. They may be more, but I think these are, I would say, three which even the entire community is kind of looking into. Of course, there may be some others. And in the end, I don't think it's going to be one of them which will win in the end, but I think it potentially will be a combination of these, so really bringing us forward. So I will start with the first one, learning from humans. And this is an area where I sort of spent already sometimes working on. In particular, we've done a lot of work with instructional videos, and it's really sort of it was the title of this talk. And so probably many of you have used instructional video. Who has used instructional video to learn something, how to do something? Yeah. So many of us, and me too. And one particular, this is an example of instructional video of someone replacing a car tire. Here in Czech Republic, we have to change car tires winter, summer every year. But if you have a flat tire and you don't know how to do it, but you have a reception, you can ask, how do I change car tire? You get a video like this, where someone is showing you, talking in natural language and showing you the different motion and the tools which you can use to change the car tire. If you don't like that particular video, you can get other videos with different people showing on different cars, on different tools. And in fact, what's interesting, that there are really millions of instructional videos online where people are showing different skills in the areas from car repair to cooking to gardening to even healthcare. So, and these videos, they really provide an exciting sort of playground of visual data combined with natural language, but grounded with real interactions with the physical world around us. But imagine we would be able to, from an instructional video or a set of these instructional videos, extract some kind of an instructional manual, which you would be able then to upload to a robot, and the robot would be able to do the task in a new environment on different objects. So of course we are not there yet, but I will show you some examples of the work and where we are getting in this direction. So this is an example of work already from a few years back, where on the left is instructional video. It's video from YouTube, and on the right, what you see is a trajectory of the human extracted automatically from the video. And it's not only the trajectory of the person over time, but also with the objects. And we explicitly in this work model the forces, the interactions between the person and the object. And what you see, the yellow arrows, are estimates of the contact forces between the person and the ground and the person of the object during the motion. Well, you may say, why is this interesting? Well, imagine that you want to transfer the skill to a robot. So this is another example of work, more recent, where we transfer this sort of shoveling motion, which is difficult. It's very dynamic motion from a human to a robot here. And how we achieve that, we do extract the 3D trajectory of the person, but then we align it with a simulation environment. And then in the simulation environment, I will show a bit more detail, trajectory optimization, to also get the trajectory of the robot and to maximize the reward, which is transporting the material from one place to the other. And so to show just a bit more detail, kind of what is involved in this. So it's a combination, you'll see, of sort of an instructional video combined with a simulation environment, with tools both from robotics, trajectory optimization, and reinforcement learning at the end. And one of the keys, so once we do get so first we transfer just the motion, and I will show that also later. In this work, we start with modeling the human, but in the end we found that it's more important to model and more universal to model the motion of the tool. So in the end, what we model the motion of the tool, this shovel here, and we transfer it into the simulation environment without the robot first, and make sure that it does transport some material. But then what we do, we run to get the actual trajectory of the robot, we run trajectory optimization, where the goal is optimized over B is the position of the robot in the space. And the V's are the velocities of the robot joints along the trajectory, the T steps of the trajectory. And it's minimizing a cost, which is sum over the different time steps. And the first is a data term, which is the distance of the trajectory with the tool manipulated by the robot from the demonstration, from the video, and if some regularization or constraint on the speed and respecting the joint limits. And this is all subject to constraints of the dynamics of the robot. So we can run an optimization like this, because directly finding the motion of the robot just based on the sparse reward from the environment was too difficult. So this is just one example how we combine these different tools to obtain in the end the motion of the robot, and we can then run this policy on the robot. And why we've seen that we can this trajectory optimization we can perform actually for different robots of different number of degrees of freedom, or even different morphology. And this is because we focus on the motion of the tool. There is no kind of imitating of the human motion. Once we get the motion of the tool, we forget there was a human. And then we can run this trajectory optimization and the whole method for different robots, even a humanoid robot here. But we don't deal with the locomotion in this work. So this is an example how we can sort of learn from an instructional video how to transfer these sort of challenging, and we have in this paper a data set and sort of several different tasks where we can test it on, how we can transfer these difficult, challenging dynamic motions. But what you see here, one of the limitations of this work is that it works so far with only stick-like objects. So after that, we spent some time of, could we really manipulate really 3D objects, like this can, for example, another from instructional video. Can we do this sort of learning from instructional video for robot motion for 3D objects? And so we've developed a whole line of work on what's called 6D object pose estimation, where the goal is to give an input image to estimate the translation and rotation, the transformation between the sort of the object in the scene to the camera. So this is kind of a fairly old problem in computer vision, but there's been a lot of progress on this problem using machine learning techniques as well. And I will show you some of the sort of recent work in this area. And also, it will be an example where we can do simulation also. So I will sort of jump, and in the end, really, there will be the work which you'll see be a combination of the first two steps, learning from humans and simulations, but I will sort of now go into the second point, can we learn from simulation of the real world? And the first point I want to make, and this was even when I was entering this area, that simulating the real world is difficult. It's just hard. And the challenge is really, how do we capture this huge amount of variety that is in the world around us? So it's challenging. Even the physics is challenging, but the sheer variety of the world is just difficult to model. But there are situations, if you manage to limit the scope of the problem, then it's possible to do interesting things. One example, and you probably have seen the impressive demonstration on walking robots. So in certain situations for locomotion, there seems to be one can do a lot for learning from simulation. The example I will show, but it's harder for manipulation, as many of you probably know. And the example I'll show you is in manipulation, and this is for object pose estimation. So if we want to estimate the pose of objects, so this scene is actually simulated. So this is a rendered scene where we take a database of more than, I think it's 50,000 objects, and we sort of render them, we drop them into the scene, 40 objects per scene, and then in this way we can render 2 million images. But what's interesting is, and this is a detail of an image, so it's high precision, it's sort of well rendered. And but what's interesting that it's because it's a rendered scene, we know everything about the scene. We know exactly the poses of the object. So we can use this data as training data to train a object pose estimation method. Like here, where the goal is given an input image, and we know a CAD model of this object, the scissors, so it's important. We can first estimate what's called a coarse pose of the object, so approximately what's the pose of the object in the image, and this is really posed as a large scale, sort of given the 2 million images learning problem, where we first learn, and you can think of it as a classifier, which looks at two images. It looks at the input image and the rendered scene and outputs one if the two are from a similar pose. And it's important to formulate it this way because the objects are often symmetric, so if you do directly regression to the pose, it doesn't work very well. So it's important to treat it as a classification problem when you can discretize the space of poses, at least approximately, and sort of these classifier outputs whether the two images are from a similar viewpoint. And from this we get a coarse viewpoint, which we can then refine, again with a refiner which is trained. We're given an input image and a rendered view from this approximate viewpoint pose. This is again a large neural network trained from the synthetic data, and it predicts the update in the relative pose, translation and rotation between the input image and the rendered view. And this way, in this sort of iterative manner, we can obtain a fairly accurate pose of the object with respect to the scene. So this method is available online. There is actually a competition called BOP Challenge, which is run with computer vision conferences, I think, every year. You can actually download this code. It's available. We've been trying to develop it so it's usable. It's one of the best systems for this problem. I think this has won this award, which is the best open source system which you can really use. You can even run it on your robot. I don't have these examples running on a robot here, but it's been run on a robot successfully. So if you want to estimate poses of objects and then manipulate them, you can easily use this software. Now, why am I talking about this in the context of learning for instructional videos? Well, because what we can do if, here this is the input video, here it's estimated pose of the object, and here what you see in the top is first in simulation, the estimated sort of the trajectory of the robot imitating this motion. You can see there is this, it does recognize this fine-grained motion, which would be sort of hard to program manually into the robot. So we can now essentially from an instructional video of someone manipulating an object, we can reconstruct a trajectory of the robot imitating or doing the same manipulation. So what do you think is an issue with this? So there is one issue, kind of a challenge or an open problem, which even when we can do this, it's still, we are not solving. So there is here we assume we know the object, the 3D CAD model of the object. But if you have some random YouTube video, well, how would you really know or the exact CAD model of the object? So we spent some time now in the last year to trying to extend this method beyond sort of these individual, when we know the CAD model. If you run it on a robot, you often know the CAD models of the objects you interact with, or you can make it. But if it's an arbitrary YouTube video, it's harder. So because we can't really get this. But there is there is a path, and the paths are actually, there are now these large databases of objects. So there is a large database of objects, and you can actually, there are actually tens of millions of the objects. We use a subset, which is about 50,000 of them, and we have developed this method which takes an input image, so detects roughly where the object is and gets a segmentation mask, and then finds a similar object from a large database. So this is a database of meshes. It's not exactly, we won't have the exact same object, but a similar one. We actually can also estimate its absolute scale using an LLM, which sort of understands what type of object it is and roughly what the scale should it be, and then estimate the approximate poles. And so what we can do is then something like this, that when we have an input video overlay from internet and then track the 6D pose, you see the object is not accurate, but we do recover approximate sort of motion of the object. We can get the trajectory on the robot, which imitates that motion, and we can actually execute that trajectory on a real robot too. I think I have one more example. But of course, we would like to scale that up beyond 1 or 2 videos. We would like to scale that up, and here there is this huge amount of data online. So we go back. So we had a paper about a few years back on build, which is still one of the largest data set of instructional videos. This is about 1 million instructional videos, each of them maybe 10, 15-minute longs, and which in the different domains, I'm showing these different areas from, I don't know, pets, animals, hobbies, and what we can do, but to apply this method, we need to understand where the action is happening and what objects are manipulated. So given this data, we've also developed now, and it's going to be published at ICCV next month, and a method for what's called grounded video caption generation. That given an input video like this, these are 3 frames from an instructional video, the output, so input is just the video, short video, about 10 seconds, and the caption is adding ingredients from a bowl and cup into a jar to mix them well. So this is the output of the method. Given the video, we caption it. But not only caption it, we identify the sort of noun phrases, here in color, man, bowl, cup, jar, and also localize them in the video. So we can process, and so this is a challenging data. As you will see some examples, sort of real world from YouTube, difficult data, but we can do this type of captioning and on a large scale. I will probably not go into too much detail in this, but we've developed a model which can really, given an input video, it produces the caption. It is kind of a generative model which, given an input, produces the caption, and then also the boxes. There are these 2 blocks, one the captioning module and a grounding, the module which produces the bounding boxes. And also we've now created, which is I think also probably the largest data set of these grounded captions. So we have more than 1 million videos which have these grounded captions with boxes in videos. And of course, if you do it on more data, it helps. On the x-axis is how much data we pre-train from. So we have an automatic method to get roughly annotated data, and then we can train from it, and you can see that it improves over time both the captioning and grounding. And here are show some of the results of the method on these YouTube videos. So here you see the colored noun phrases which are localized by the boxes in the video. You see the variety of viewpoints, the variety of objects, and we have 1 million of those. And just to sort of get, so that you get the scale of the data, I did a histogram of just the verbs, yeah, and so you see that some of the more generic, like adding, it's 100,000 times in the caption. So, and And the one which I want to show you, and these are some of the results which my students have generated last night, because this is a project which is ongoing still. So we looked at pouring, and we are wondering, well, how much pouring, videos we'll really get. But as you see, there's more than 12,000 in that data set. So, but he did what we could. We can take those videos with captions and boxes, and we can then plug it into this pipeline for this object pose estimation, and here are some of the results. This is about 50 videos which we got. We're still working on the method there, but I think this is sort of giving you what kind of results one can get from this analysis. So you can see the overlaid trajectories of objects, approximate, of course, because we don't have exact models. These are approximate models, approximate trajectories. And he even managed to get the approximate trajectories of the robots imitating those motions. And this is just pouring. So our goal is now to go and scale this up and do it for other motions. Of course, it's going to be challenging, but we do think we can make some progress. And you may now think, well, pouring is relatively easy. You can still kind of, with the robot, grasp the object, and then sort of, it's not a difficult, and you can still model it physically with the tools which we have. And it's true. So, but I do think there are many actions which we can still get interesting motions, learn motions, how to do them from the videos. But there are many other actions which are hard to model and physically and simulate. Folding clothes, for example, or in cooking. So you have lots of actions like cutting, which are, peeling, which are hard to model physically in the simulator. And because of that, there is a whole line of work on actually learning simulation, what's called world models. You may also have heard of those. I do have some citations later. What I want to show is an example of work which we did over the last 2 years on, and here is an image of a pineapple. And what we would like to have is to see how this particular pineapple would look when it's peeled on chopping board, so instructional language, in a blender, or when it's sort of is a smoothie in a blender. So instead of, so of course modeling this explicitly in simulation would be physics simulation would be very difficult, but could we imagine how this would look like? Or can we train a model that could imagine how this scene would change if you do this? And of course, you can do with the generative models. I want to outline the difficulties. So you can say, well, I can now generate with, nano banana, almost anything. But what's hard in this, that it's really, the model is changing this specific scene. Yeah. So, and the model which we've developed, I will not go to details much, but it's really trained from this instructional video. So it's really looking how the world is changing in a video to do these changes. And of course, we can apply to the different objects. So these are the same instructions peeled in a blender, smoothie for a different object like an avocado. So this, in the first paper, which appeared last year, we had a model which can do just like a one change. In this case, we changed the changes. But we have a paper which was just appeared CPR this year, when we can actually do a given an input image and instructions, we can do like a long sequence. So if you know the current world models, they can do maybe 30 seconds of a video. It's a continuous video. We cannot do continuous video, but we can do really like a long sequence of steps, which in an instructional video may correspond to 10 minutes, for example. And these are so fairly complex interactions, which would be very hard to model physically. I will just flash this model which we've developed. So it has an input, the natural language description, and the input scene, and the output are the frames corresponding to the different language instructions. But what's important, so these are all like generating individual frames, what's important is that there are temporal connections. There are this temporal attention between the different sort of blocks. So what here in the previous work, you can see the plate could change. The color of the plate is changing if you do kind of two different generations. There's no temporal consistency. In the new model, we do have temporal consistency, so it generates kind of consistent scene. And we can even prompt it to like generate 2 frames, but more frames. And what's very interesting that when you ask it to generate 3 frames, it suddenly sort of generates really like an intermediate frame, which would correspond to the intermediate state of the world. So this is a model which we have now. We are now looking how to incorporate it as potentially, say, a reward function in robotics, but we haven't done this yet. But we are excited about this. I'll show a few more examples of like a long sequences. So that's different from the current world models, which can do short videos. We can do long sequence, but only sparse keyframes. We want to combine these to be able to do long generation over, and of course target it to robot motion. We can evaluate, I will not go into details of this. This model really performs better than some of the other techniques. What was exciting to see and interesting that actually we can compare it when we have gram truth source sequence. And in some cases, this was like it's a human raters. They preferred our output, so in 42% over the source sequence. And what we saw is that the source sequence sometimes people talk about things which they don't actually show in the video. They say, well, I take the chicken from the fridge, but they didn't show it. Whereas our model generates everything what is required. There are some failures. Of course, how well it works depends what is in the training data. So I like specifically the example at the bottom where it says you want to slice this apple, so it produces kind of the emotion when someone is cutting it. But then, because it hasn't seen any slices apple, only it's seen, this is for a new object. It hasn't seen apples in this particular case, but it's seen probably onions. So it sort of produces how an apple could look like when it's sliced, but it's sort of more looking like if you chop onions. So I think there is limitations. It really depends on what training data you use. I want to say that there is this exciting work which is related on these world models. I'll just citing here too. They usually are shorter sequences, maybe 10, 20, 30 seconds, but they have continuous motion. Okay, and I'm getting into the, and I'm a little bit running out of time, but I want to tell you about this last direction, running from other machines. And I find this very exciting. And just the vision is, and I think really that's where we will get the most of the scale. Imagine now that we can really have the robots at different places and doing different things in different environments, and they could somehow be able to share the sort of the learning process or share the, and I think what I want to get to is that, well, maybe they could share the data. Yes, we can capture more data and store it and learn from it, but what I feel I think really the breakthrough will be where they will be able to share model parameters. So imagine each of these robots will interact with their environment, and once they succeed, they will take the model parameters of that skill and just upload it, and someone else could use those model parameters. We don't have this technology yet, but I think it will be very interesting, and it's a direction where we are looking into. Can we enable this kind of a sharing, not necessarily the data, but on the level of model parameters? Of course, we are not there yet, but I will show you some sort of directions where I think it's interesting where it's heading. So first of all, there is sharing of data is really taking off. So this is an effort called OpenX, where it provides kind of a common format where different people around this mostly research lab around the world can actually put and share their data. So if you're working on robotics, you can share the data with others in this sort of common format. And there is really now 22 different embodiments, more than 500 skills, 60 different data sets. Of course, different robots, different embodiments have different amount of data, depending how many people work on it. And so that's why I want to mention one example subset of it is called a Droid data set or Droid platform. It's a specific setup which involves the Panda robot. There's a specific setup of 3 cameras, 3 viewpoints. And for that, it's probably the most data at the moment for a single platform is for the Droid platform. It has more than 70,000 episodes, different scenes, and captured from different institutions in different buildings. And it's about more than 80 tasks. So I think this is one of the probably the most data there is for this Droid platform. This is really this kind of a Panda robot with 3 cameras, 2 outside, 1 on the wrist. With specific gripper. So if you really want to use that, you need to kind of get this setup and build it. And I think then you can reuse the data which is captured by others. And a lot of the data is captured by teleoperation. There is like this teleoperation device. So we have this setup in the lab, which is just in the next building. We have the robot with the same gripper, with the setup of the cameras. I don't think you can see the cameras. For the teleoperation, we've built this teleoperation device, which imitates the sort of kinematics of the robots. You can see the scale of it. Here I'm sort of operating the robot, and we can use that to capture the data. But now, so what would you do with this data? So you can train now what's called a vision language now action model, and probably many of you are, or some of you are working on this. So it's really taking a pre-trained vision language model. You've seen vision language models which are doing this grounded caption generation. These are different pre-trained vision language models which take input, kind of images from this camera, a prompt, what to do. They are pre-trained, but they are pre-trained not only vision language data, but they are pre-trained on this robotic data. So they see images with the motion of the robot, and they are trained to generate a trajectory given the image of the scene and the prompt. They actually output of this is actually a trajectory of the robot. And it's a way how one can really take advantage of the data, and then that robot then is prompted by a prompt to do something in a new environment, and I'll show some examples. This is and there are several of these models which are available, like this is a Pi0 model, which one can take and run it. So these are examples, sort of running this model in our lab. I'll try to maybe show one example. So you see this one of the external cameras, one of the cameras on the robot. Say put banana in the box, and it grabs the banana and puts it in the box. And the model is just trained on tens of thousands of simulations. I think this one may be trained also on other embodiment. How much it benefits, it's unclear, but this model is trained. But it can, banana, it's interesting that it can also fold t-shirt. I'll show an example here. And this is zero shot. So did no training on our setup. We just took it and just put it. We had to get the gripper. So before we got this exact gripper, it just didn't work at all with other grippers. Once we got the gripper, and we think it's partly because the gripper is visible in the image. So if you have different gripper, the model just doesn't work. And so these are all sort of zero shot. You ask it to do something and it does it, but does it only sometimes. Sometimes you ask it to pour from bottle, and this is the video at the bottom. And here, for some reason, just the robot can't do it. And so and there are some cases where it works, it's nice, sometimes it doesn't work. So we are thinking, well, why does it work in some cases? So it's a way, so this vision language model is a way how to ingest a potentially large amount of data into a robot. But how do we, so I think it's potentially a way towards major progress in robotics, but the issue is that we really don't know at the moment how it works, when it doesn't work. You have no guarantees. So kind of after seeing this, we embarked on this path of, can we evaluate these vision language models in some, what are their failure modes? How do they understand human instructions? And most importantly, can they generalize? What is their generalization properties? So we've developed, and the paper is not out there, but we are kind of finishing that. I'm hoping it should come out really by the end of September. We are writing it. We sort of developed what is called a realm, high fidelity simulated benchmark aligned with the Droid platform. So we're using sort of 7 base skills, which you see here. We have sort of simulate 15 distribution shifts, which are visual, different kind of viewpoints and other sort of visual changes. Semantic, we sort of have the prompts in different language written, and also behavior is like a change of the mass and weight of the objects, change of the shape, and sort of it can measure now, quantify how well the model works. So of course there are other sort of recent works which are also trying to evaluate, and I think they are nice, but we think our has sort of 2 special things. First of all, we really put a lot of effort, and it was hard, is to have it aligned like a real to sim aligned with control. So really the control of the simulation is really matched to the control of the real Droid platform. So this took a lot of effort, and also is sort of photorealistic or close to photorealistic. And also we used everything. We have the largest amount of visual shifts and these behavioral shifts than compared to other existing simulation platform. And so once it's done, we plan to really put it online so that others could also evaluate these models. We can measure the performance. I think once we start measuring the performance of these models, we will be able to make progress. In computer vision, we've seen that with benchmarks, they really enable huge progress in the field. I think in robotics, one of the issues is that many people have their own platform. It's hard to measure progress across the community. These are examples of the real tasks on the real robot. Here are examples in the simulated environment. And here are examples of these distribution shifts. On top is visual, behavioral, and semantic is mostly in the language. You can say the same things in slightly different ways. So I'm really running out of time, but there are some interesting observations. And I think on a high level, it is sort of surprising that the models are kind of sensitive to like the lighting. In some cases, they are very sensitive to lighting. They shouldn't be really because they've been trained on quite a lot of data, and they've seen a huge amount of pre-training data. They have poor spatial understanding. You can tell it, put it next to something that doesn't understand well, for example. And some tasks poorly generalized. There are some successes, especially in tasks which would be considered difficult, like folding cloth, for example. And they could do it, and with a surprising, you can put a different t-shirt, the model will still do it. And some tasks are performed robustly. So I think we want to really quantify and sort of put it out and see our observations. Seems to be consistent, are appearing now even blog posts and observations by others. But I do think that when we really start measuring how well they work, it's going to be a path toward more progress. And I think the simulation is one part of the story. I think in the end, one really needs to validate in the real robot. And I think there is this very nice effort into distributed evaluation. On the Droid platform, we are now also becoming part of it, and this means you can train your own policy, and you can actually submit it here, and it will be evaluated at different places on different Droid platforms around the world. We will be also evaluating. You can also join the effort. Also, if you have a Droid platform, you can also evaluate your and other people's policies in the real setups. And I think it's a very nice way to really, probably first you go to simulation, and then you can evaluate in the real setups so that we can together measure progress. And with this, I will finish. I think it's a very exciting time now to be in this area of robot learning. I think there's a lot of sort of progress. I think more we'll see happening because we're beginning to have these tools which can incorporate large amounts of data. We'll have starting to have large amounts of data. I do think that short term we do see progress in applications. I think applications are important in specific domains. But overall, I think long term we really, there's this quest for long-term autonomous learning of these robots. Reasoning, I haven't discussed this sort of learning, in lifelong learning, for example, reasoning, planning complex actions, and interacting with the environment. And actually, last time I'd like to really thank my team. All the results are thanks to them. Thank you very much for the attention.
Okay, thank you. Wonderful. Thank you very much, Josef. We have time for questions. Please raise your hand. Lorenzo.
Hi. Thank you very much. Very exciting report. I wanted to ask you a little bit how to put together the different things you showed, because you showed, like, for example, thank you. You showed, for example, annotating videos of the instructions, including extracting the trajectories of the objects. And then on the other hand, you showed the visual language, the VLA models, that basically if they receive only the instruction, they should be able already to perform the action. So ideally, they will not need the trajectory of the object. So how would you put the things together to think, in the end, you have a YouTube video, you give it to the robot, and it does it, right?
Yeah. So it's I think where and thank you very much for the question. But I'll be here around after, so I'm happy to discuss afterwards as well. It's really those instructional they shoot, and that's what we are working on. They can become training data. So all these vision language action models, they are trained on trajectory. So they do see a video input and a trajectory of the robot. Yeah. So you require this information, and this is scarce. It's very expensive. I didn't explain that. It's very you have to really. There is this painful process where people kind of go and teleoperate the robot to obtain the data, and at the moment the students doing it, but it's hard to scale that. And I don't think it's going to be a complete story. but I think if we augment, so our plan is to augment as much as instructional video as possible with trajectories of the robot, or with some 3D information. We'll need to see what really we require. Maybe boxes are enough. Maybe objects, 6D object poses, or the whole trajectory of the robot, and use it as additional training data for training, and hoping we obtain by that much more generalization of the robots.
Okay. More questions? There is one there.
Yes, please.
Hello. So first of all, thank you so much for this wonderful presentation. What I would like to ask is that in the first works you have showed, it was directly trajectory following from 6D pose estimation, etc. But in the annotated work, which you have also discussed earlier, so we have, for example, the task opening the bottle. Mm-hmm. So, but in most of the videos that has been trained on, like the human first like squeezes, let's say, the bottle and then opens the cap. But optimally, for example, if a robot is stronger and has less slippery hands, it can directly open the box with just a pop. So what I would like to ask, probably I overstated the question, sorry about that, is for that work, is it more important to follow the trajectory or follow the goal? Mm-hmm. So what's the distinguishment between the goal and the trajectory of the goal achieving it?
Yeah,
in the work?
I think it's a very good question. It's the work which I was showing on the generation, actually the way we think about it is really generating these states of objects and how they change is really the goals. And of course the robot may have a slightly different way of achieving the goal. Yet at the same time, we see in the learning, it's hard to give the robot just a sparse reward and just open. We can measure whether the bottle is open using visual sensor, but it may, if you just give it, the robot may take a very long time to discover how to open it. So the way, and this is really a hypothesis, we need to show it, is that the human sort of videos will show as will serve as initialization. Yeah, the robot, okay, I could do it this way, so they will see a demonstration how to do it. But of course, they will then run like a reinforcement learning. Once they have an example, they could optimize it to do better. And we've seen that, and some of it maybe could be done in simulation if possible. We've seen that in the shoveling example. So the transfer of the human was was not very good, but then we ran a reinforcement learning to maximize the transported material, and has really improved the trajectory of the robot in the simulation.
Like an apprenticeship learning, where the apprentice has actually, okay.
Yeah. So I think I think of it, the human demonstration, more as an initialization, which will kind of help guide the robot, but then hopefully they will be able to improve.
Thank you so much.
Okay, Giulio.
Yes. So thanks for the presentation. Very nice. The role of vision is definitely a key, issue here. On the other hand, these educational or informational videos for us are very useful because we have a memory of an interaction with objects, with reality, and so this is just a guide. Recalling our memories from past experiences. But for a robot, there is still no memory about touch, about haptics, about this kind of information that you can only grasp by doing. So how can you think of adding this missing part?
So and again, I think it's going to be in the end, I think it's going to be hypothesis, it's going to be a combination. And so really all the work in visual language models, which I was showing at the end, maybe I should reorder it, it's guided by these teleoperated experiences. So the robot does see how, and it does experience, also guided by the human, the interaction, the physical interaction with the world. I think these instructional videos, the issue is, and I think, they require, some of the latest models, they require hundreds of trajectories to do basic tasks, and then you do it, and you move the bottle by a little bit, it can still do it. If you replace it, if you move it too much, it won't do it, and if you kind of replace it by a different bottle, this one, it will also fail, because it's really just trained for this bottle. So the training, just the human demonstration in the teleoperation is not scalable. That's why I think the instructional videos, they will bring this huge variety of the visual world around us. And they have this visual variety which they will bring on top of it. So, which I'm hoping that in the vision language models, they could be this visual information could be connected with the kind of physical trajectories of the robot. So I don't think they're a complete part of the story. You're very right, but I think they are an important component which will bring in the generalization. That's my hypothesis, which we need to validate.
Physical interaction is a personal kind of information, and you only get it in the same way from the same system. If you change the robot, it completely changes everything. So in that case, generalization would be very hard. If you don't have the concept of the action that you are doing and some kind of past experience. But definitely,
let's discuss more about. We had a lot of interesting discussion with Matěj on this as well. Because in vision we feel kind of very empowered by lots of data and generalization, and it's very, it's a big question whether some ideas will transfer to robotics. Because Matěj also, as you're saying, that the embodiment is key. There is going to be never a transfer across embodiment. I'm not sure. I think we need to try that. Maybe, and I think that's what we could hope for potentially as at least a bit of compositionality. That's what we see in the visual domain. But of course, it's a very open question, and I'm excited to see how it's going to pan out.
Thanks a lot. Thank you.
Okay, so we have to close here. We're running out of time. Thanks, Josef, again.
Thank you.